Okay, so we're going to be solving an equation. Cosine of theta is equal to 1/2. Notice there are no domain restrictions. They're not saying please solve specifically for angles within a given boundary. So if you never see specified angle boundaries, what they're really saying is solve for all theta. For every angle that would make that true. Now, of course, angles don't then have to be bounded between 0 and 2 pi. So let's just realize, what is the sign of this value? It's a positive value, correct? And we can come back to all students take calculus. Let me ask you this. Where in these quadrants would cosine be positive? In the first quadrant and in the fourth quadrant. That's what these letters are referring to. All, sine, tangent, and cosine. Those are the functions that are positive in those given quadrants. So what's going to happen then is I need to answer with a particular reference angle. What reference angle would cosine equal 1/2 at pi over 3? So I'm going to say, you know what? I could be in the first quadrant. That could be pi over 3, but who's to say that it only could be pi over 3? It could be anything coterminal. If I continued to add 2 pi k, where k would be an integer, that's what this symbol right here, z, is, you could say, hey, I could continue to add 2 pi radians as many times as I'd like. That's what that 2 pi k is really representing. K could be 1. You could say make 1 revolution around the circle and then add pi over 3 to it. K could be 2. Make 2 revolutions around the circle. You could also subtract 2 pi as many times as you'd like. That would be going in an opposite direction. That's not our only answer, though. We could also say, what about this fourth quadrant? How could we write an angle in the fourth quadrant? What do you think? 5 pi over 3, I heard someone say, you're right, plus 2 pi k, comma, k is an integer. Now, every once in a while, kids feel dejected. They look the answer up in the back of the book, and they'll say, the author wrote 5 pi over 3 plus 2 pi k. I didn't. I wrote negative pi over 3 plus 2 pi k. Would negative pi over 3 plus 2 pi k work?
Yes, sir.
Yes, definitely. And I think, sometimes kids will realize, oh, yeah, wow, we don't really have any angle boundaries here. Negative pi over 3 would be represented here. I want to tell you that if we let k equal negative 1, we'd get 5 pi over 3 minus 2 pi. That, sure enough, is going to get you your negative pi over 3. So, I just want to tell you that this is all represented. As we take a look at number 2, though, or, the second problem, it's really not numbered, you can see that there are angle boundaries. We're not going to be free to go as large as we'd like or as small. We're definitely going to be just between 0 and 2 pi. So tell you what, I'm going to subtract pi over 3. Simultaneously, I'm going to divide by a 2 here. You could have gotten that pretty much all in one step. But here we go again. Sine is negative. The big question is, which quadrants could sine be negative in? The third and the fourth. Because only tangent is positive in the third, only cosine is positive in the fourth. Now, I'm not going to have answers with 2 plus 2 pi k here, because I'm only between 0 and 2 pi. What reference angle would sine have root 3 over 2 in? Pi over, not pi over 6, pi over 3, right? So we could look over here and say, how do we have a reference angle with pi over 3 in the third quadrant? That would be an angle of, well, here's pi, which is 3 pi over 3. If you go pi over 3 past, you'd be at 4 pi over 3, right? And then what else? Over here, you'd be at 5 pi over 3, right? So just 2 answers Remember, when you had pi over 6, sine of pi over 6 is when you have a half, right? We doing okay? All right, let's keep going. This is where it gets to be a little bit trickier. And what's happening is you're going to see that the argument of sine, the inside part of sine, is now no longer just a theta. It's 2 theta. And when you get any variation of the argument, and you're going to see that in the next problem as well, my suggestion to you, and this is just a good general way to solve, is to say momentarily, let's let W represent that interior of the trig function, the argument. Keep it as a single variable and just try to solve that. And right now you could say, well, wait a minute, sine of W equals 1/2. This is a positive value. Where is sine positive? Which quadrants? In 1 and in 2. So what reference angle are we talking about? At pi over what? 6. Now, I'm going to do something that's probably going to seem contrary to what I did earlier. I'm going to say over here is your pi over 6. And then I'm going to say plus 2 pi k. Now, immediately, somebody could understandably say, now, Mr. Dobner, wait just a second. Didn't you see the angle boundaries? You're only going between 0 and 2 pi. Why in the world are you writing plus 2 pi k? The answer is, and I hope you're going to see in just a moment, when the argument is changed, you're potentially changing the period of this function. And that's exactly what you're doing. So you might just get multiple answers as opposed to a single variable. When your argument changes, try to write your answer in general. By the way, you could always write your answer in general and then adjust. We'll go to that in a moment. There's this other quadrant over here. What would that be? W would be 5 pi over 6 plus 2 pi k. Now again, that can seem so strange, but what was W again? 2 theta. And you'd say, okay. Look, I'd have 2 thetas over here. Now, what I want to tell you is that solving for theta means take half of everything here. When you're taking half of pi over 6, what's half of pi over 6? Dividing it by 2, you'd get pi over 12. Plus, now wait a minute, you take half of the 2 pi k and you're at 1 pi k. You see that? And then you come over here, you'd say, well, I'm going to take half of every item here. You'd say, what's half of 5 pi over 6? Answer, 5 pi over 12. And then you take half of 2 pi k, you get pi k. Now again, this might seem very contrary to what I was talking about earlier, where kids are saying, you're like writing out an infinite number of answers when you have this. Agreed, but listen, right now, I can come back over here and say if theta was equal to pi over 12 plus pi k, and if theta is equal to 5 pi over 12 plus pi k, I only want answers between 0 and 2 pi. I could say what happens when k is equal to 0. What answer would you get? Pi over 12. What happens when k is equal to 1? All of a sudden you'd say, well, I'd get pi over 12 plus 1 pi plus that. That's 12 twelfths pi plus 1 12th pi is 13 pi. Look how easily you would have forgotten that 13 pi over 12 if you didn't write the plus 2 pi k. Do you see what I'm talking about? See, your period is changed when you put in a 2 theta. In fact, you're doubling that cycle. Your sine wave is going to be, the period is actually cut in half. It's going to go through a lot more cycles. So you get more angles in this regard. You do the same thing over here. Now, by the way, if you had k equals 2, that's too big, right? 2 pi plus pi over 12 is going to get to be too big. K equals 0, you'd say, well, I'm going to get 5 pi over 12. If k is equal to 1, well, you'd get 5 pi over 12 plus a 1 pi, but 1 pi is 12 twelfths. I think you can see you get 17 pi over 12. You don't get two answers. I think that's what so many kids get surprised about. They'll say, well, there are two quadrants, so I'm going to have two answers. Ironically, you're getting four answers. And unless you make this adjustment, you're going to have some difficulty getting all of them. We doing okay? All right. So, look, I know this can look a little strange too as you go to this next equation. You've got the tangent. Tell you what, I'm still going to do tangent of W. I'm going to do the tangent of W here. And I know the argument, kids can correctly point out that the argument is not changing the period of tangent, and I totally agree with that. That's absolutely true. But this is an important thing to talk about. Where is tangent positive? Which quadrants? First and third. Now, I know you've seen this before, but what you need to see is when you have a first and a third quadrant solution, you can see that the two angles can actually form a straight line. Now, how many degrees do you have in a straight angle, a straight line? 180. And in radians, that would be pi. So, look, what you could do, and by the way, when is tangent equal to 1? When you're at pi over 4. Look, what you can do is just combine opposite quadrants by saying a straight line connects them. I could say plus 180 degrees K if I was in degrees. Why do we do this? This is so elegant and simple to write out your solution set. Now what? Well, from here, you could say this is theta minus pi over 2. Okay? So I'm going to very quickly just add my pi over 2 to both sides. And let's see what would happen. Well, this would be 2 pi over 4 plus 1 pi over 4 is 3 pi over 4. And guys, if perchance they said just answer every possible angle that would make this true, our statement right here would do the trick. It would, this right here is a nice, concise way to represent every angle that would ever make that true. But look, we're going to go between 0 and 2 pi. So we're going to say, let's let k equal 0, and we get 3 pi over 4. By the way, you can't let k equal negative 1. You'd get something negative. You could let k equal positive 1, and you get 3 pi over 4 plus 1 pi. That's 4 fourths plus 3 fourths. Your second answer is 7 pi over 4. Look at that. So k equals 2, you get to be too big. Right? So k equals 0, k equals 1, k equals 2 is just too big. Okay? Think we doing okay? Yeah. This next problem, you want to make sure you're on the radian mode. We're solving an equation. Tangents equal to negative 2 only between 0 and 2 pi radians. Let your y1 be tangent. Let your y2 be negative 2. Left side is y1, right side is y2. I'm going to go between 0 and 2 pi. My y scale, I went from negative 3.1 to positive 3.1. Of course, you can get some different boundaries to get this graphed out. But what's going to happen is, you can see this is the line y equals negative 2. It looks like there will be 2 points of intersection. What you do is you go second calculate, and you'll hit intersect. It'll say first curve. You can hit enter. Second curve, hit enter. It'll say guess where you think it crosses. Well, we can come right over here. One of the answers evidently will be 2.03 radians. The other, if we were to get that thing graphed out, The second point of intersection would be 5.18.